In this video lecture, I'm going to go over Chapter 17, Practice Exercise 7b. It says calculating the pH at the equivalence point. So something to remember, when we're at the equivalence point, definition, we have to memorize this. The moles of whatever is in your beaker, acid or base, equal the moles added from the burette. So in this case, we are given 40 mils of 0.1 molar NH3 titrated with 0.1 molar HCl. So what that tells me that I have in my beaker my NH3, so 40.0 mils, 0.100 molar NH3, and added from the burette, I have 0.100 molar HCl. And we're told that we're at the equivalence point. That means the moles of base in the beaker, which I can calculate, because volume in milliliters times molarity gives me moles. And then I'm told I'm at the equivalence point. So that means 4.00 moles of HCl have been added. So if I added 4 moles HCl, let's figure out what that volume is. So I use my molarity to convert. It's given 0.1 molar, so that's 0.100 moles HCl for every 1 liter. And so what that ends up with is 40 milliliters of HCl must have been added to reach our equivalence point. So now I know the moles of each, and I'm going to now write my reaction. So the reaction between NH3 and HCl is going to produce ammonium chloride. So NH4 plus and chloride. And I'm looking at an IC end box with my millimoles because I see a reaction is occurring in the forward direction between a weak acid and a strong base. So, a quick review. When to use IC end with moles or millimoles. So the first case, if you have a strong acid plus a strong base reaction. The second case, strong acid plus weak base reaction. Third case, weak acid plus strong base reaction. These would be our titrations. Also, we use the IC end if we have a buffer plus strong acid or buffer plus strong base. Also review, when do we use ICEQ with molarity? So we really had, in Chapter 15, any given equilibrium reaction, right? We have I, initial is given, equilibrium is given, and K, we are going to be given to and asked to find the third. The other reactions we learned to write ourselves. Weak acid plus water equilibrium, or weak base plus water equilibrium. So hopefully that's a good review on when we use ICN with moles or millimoles and when we use ICEQ with molarity. So back to this problem. We're using ICN with millimoles because I've got a weak base and a strong acid reacting in the forward direction. So I know for both species I have 4.00 millimoles. Nothing is mentioned for the product, so it's 0. The change, we're going to subtract the smallest number, which in this case is 4. And then in the end, I've used up all of my reactants, which I know is the case because I'm looking at an equivalence point, so they're always equal. And I end up with 4 millimoles of NH4 plus and 4.00 millimoles of chloride. So right away, I remember that chloride is the conjugate base of a strong acid, so it does not affect the pH, so we can ignore it. Review chapter 16, the acidic and basic properties of salts, to go over that. And I then also have ammonium. And I recognize that ammonium is the conjugate acid of the weak base ammonia. So that's an acidic cation. So it's an acid and it's a weak acid. It's not one of our strong acids that we memorized. So a review, how do we get the pH of a weak acid? Well, I know I have to perform a hydrolysis reaction and do ICEQ with molarity. So to get the molarity of my ammonium, I take my millimoles of ammonium and I have to divide by the total volume in my beaker at this point in time. So remember my total volume, I had 40 mils of the base, and I added 40 mils of HCl to reach the equivalence point. So my total volume will be 40.0 milliliters of the base that was in my beaker, plus 40.0 milliliters of the acid that I added from the burette. So my molarity of my ammonium is 0.05. So 0.0500 molar ammonium. So now I know the molarity, so I can look at my equilibrium reaction. And I know I'm going to do that because in my beaker, at the end, I have chloride that we ignore. It doesn't affect the pH. I have ammonium, and I have water. So the only two things that can react are my ammonium and water. And this again is my weak acid hydrolysis reaction. So I produce NH3, the conjugate base, and hydronium. And this is a Ka reaction, which I know I'm given a Kb. I was given a Kb in, I think, the previous problem. So we have Kw over Kb of NH3, or you'd be given that on the cover of your exam. So ICEQ with molarity. So I have 0.0500 molar. Water we ignore. 0, 0. Minus X, my standard ice box. The reason I'm subtracting and adding X is because it's an equilibrium reaction. So remember, if I have an equilibrium reaction, I don't know how far the reaction is going to shift, but I can see it's a 1-to-1 mole ratio. So I use up reactants and I make more products. And now EQ, I add up the columns, 0.0500 molar minus X, X, and X. Now we stop and think, how do I solve for X? Well, I'm given Ka, so let me add that here. and we were given Kb for NH3 equals 1.8 times 10 to the negative fifth. So that's what we use to get Ka. So Ka is going to be Kw, 1 times 10 to the negative 14th divided by Kb, 1.8 times 10 to the negative fifth. So when I solve this, I have 5.55 times 10 to the negative 10th. So I'm taking one extra sig fig through, I'll round at the end. So now I can use that K value to solve for x. Okay, so I'm going to use my K value to solve for x. So I know that my Ka value is going to be NH3 times hydronium divided by NH4 plus. So I have 5.55 times 10 to the negative 10th equals x times x, which is x squared, divided by 0.0500 minus x. Going to assume that x is small, which will be the case because our k is very, very small. And now I can quickly solve for x. So with algebra, x equals the square root of 5.55 times 10 to the negative 10th minus 0.0500. And putting that into my calculator, I end up with 5.28 times 10 to the negative 6th. And always a good idea to do the check, is x small? Compared to what the number it was being subtracted from. And we can see that it is. But just to check, I take my x value, which is 5.28 times 10 to the negative 6, divided by 0.0500 times 100 to make it a percent, because remember we're looking for 5% or less. So on the calculator, 5.28, second E, negative 6 divided by 0.05 times 100. And I got 0.01%. So yes, it is small. Now we want to go back and solve. So I'm trying to get my pH. So I see that I have X, and I see that X does indeed stand for hydronium at equilibrium. So now I can go ahead and solve my pH. So my pH equals negative log of hydronium at equilibrium, which is just negative log of my X value, 5.28 times 10 to the negative 6th, which, and I know I've had two sig figs there, so it gives me a pH of 5.28. And that would indeed be our final answer for pH. So just a quick recap of this problem. We're told we're at the equivalence point. So I know that means the moles in my beaker equal the moles added from the burette. I was given a volume and molarity of ammonia. So I multiplied to get my millimoles of ammonia, millimoles there of ammonia. And I know the definition at the equivalence point, I have the same number of millimoles of HCl. And that conversion then is milliliters for millimoles. Sorry, I had that written down wrong, but it did not change the math. So we have 4 millimoles of ammonia, which means I've got 4 millimoles of HCl, which resulted in 40 milliliters of HCl added to reach the equivalence point. So I write my reaction, my weak base and my strong acid to make ammonium and chloride. I see end with millimoles, so I've got 4 for each. So at the end, at the change, I subtract the smallest number, add it to the other side. At the end, I use up my reactants. Chloride, I know doesn't affect the pH, so I ignore it. Ammonium is the conjugate acid of a weak base, so it's a weak acid. It does make the solution acidic. To get the pH of a weak acid, we have to first get the molarity. So the millimoles in the beaker at that point in time, at the equivalence point, divided by the mils of the solution in the beaker when you started, plus the volume of whatever was added from the burette. So the molarity of my ammonium is indeed 0.0500 molar. And then to solve for the pH of a weak acid, your hydrolysis reaction we write ICEQ with molarity, subtract x and add it to the other side because I'm looking at equilibrium. So equilibrium, we always have our minus x plus x plus x. This is a Ka reaction because I'm producing hydronium. I'm looking at a weak acid reacting with water. So I can, with a given Kb, it's given here, I can solve for Ka. And once I have Ka, I can then solve for x. I check to make sure that x is small, which it is, so we do not need to go back and use the quadratic formula. And now I go back to my ice box. I can see that my x, again, is at equilibrium, my hydronium. So my pH is just a negative log of that, which is 5.28.